TDs anymore, or the players.
There you go. All right, should be going.
Okay. So what I put together is based on the list of questions that was submitted. I took some creative license in how I chose to group the questions and put some things together. And a couple of questions I won't answer because they don't need to be answered. The one question that I will just answer right off the bat was the one about, because I didn't do a slide for it or anything, but temperature and water droplet size relate. It's not really a direct correlation between temperature and water droplet size. Water droplet size is any droplet in a cloud or falling as precipitation. That drop size is determined by first, any cloud droplet has to have some sort of condensation nuclei that water molecule is going to adhere to. Without something that is dust, aerosol, salt from the ocean, without that, a water droplet cannot form. So water molecules have to have something to adhere to start to become a droplet. Then to get bigger, there is a process called coalescence. So basically like little droplets eat bigger droplets or eat other droplets and get bigger. So if you think about like in a thunderstorm, a lot of updraft, a lot of energy going upward, lots of opportunity to run into other raindrops and get bigger, kind of like a Pac-Man kind of thing. And then they get heavy enough, they fall back down. But even as they're falling, they're getting bigger. So temperature is not really, there's no direct correlation between temperature and droplet size.
Okay.
One question done. So, it's a squeaky chair.
Here, no chair.
No, you're good. I'll just not rock around so much.
It's okay. Here.
Get this terrible chair out.
So, okay, and I don't want to take us off topic, but I'm thinking about, does that mean that there are certain places on the globe where water droplets or moisture can't form because there's nothing for it to adhere to?
Theoretically possible.
Okay. But enough places, I guess, have small enough. Gotcha.
Yeah, exactly.
Gotcha. Okay.
Yep. Yeah.
Mm-hmm.
And in this day and age, think about how much pollution there is in the air, aerosols. Yeah. Like there's plenty of opportunity for a water molecule to latch onto something and grow into a droplet.
Gotcha.
So what I did to organize thoughts for tonight, it was a really good list of questions. And what I put together is we'll spend a little bit of time on air masses, pressure systems, fronts, because those all go together. A quick little overview of heat transfer, because I know there's a question about convection and a question about vorticity. So we'll talk about heat transfer processes first, and then we'll talk about advection processes, which is vorticity is one of those. So we'll talk about that. We'll spend a little bit of time on marine layer dynamics. And then at the end, I have some radar signatures we can look at and talk a little bit about tornadic formation. I think that was it. So, beautiful scene last night across the U.S. It was actually kind of quiet last night in terms of thunderstorms. There wasn't too much going on. First question was air masses. And I think the question itself, just to make sure that I cover all the right details. What distinguishes air mass from hot or cold, and how much does it take to distinguish it? And I framed the answer to that question up a little bit differently. So air masses are classified by two things. One is humidity, and the other is temperature. And it is the humidity and temperature of the source region in which they are formed. So for humidity, it could be maritime or continental, maritime being over the ocean, continental being over land. And then temperature, and there's no equatorial ones on here. Obviously, those would be down here. But we have tropical, closer to tropic regions. The polar ones are up kind of above 45 north. And then Arctic is way up north, polar, which is funny, polar type air, but it's actually Arctic air, very far north. But during wintertime, continental Arctic air masses will actually come down, especially in the eastern half of the U.S., and make it very cold. So that is air masses. There's not like a hard and fast rule of what distinguishes, there's not like a continental polar has to be this like temperature at the surface or have this humidity level at the surface, but they take on the characteristics, like I said, of the source region that they come from, and the longer that they can sit there in place, the stronger that characteristic of that source region is. So if you have a continental polar high that'll, I'm thinking about wintertime, this often sits here almost as like a semi-permanent high, and it will make it very cold, and it will just continue to be cold. It doesn't really ever moderate, especially in the wintertime. The longer they can sit there, the longer that it'll just stay cold.
I think the question was kind of oriented around like we see a warm front, right? Mm-hmm. And like the question was like, how much warmer is the air mass behind it, you know? Mm-hmm. And that's, I think, kind of a misnomer of looking at it, because you're looking at something else to distinguish the front, right? Mm-hmm. And I think
that is like well, we'll get there in a second.
Yeah. Okay.
Yeah.
Right.
Good question.
Yeah.
But yeah, it's really these air masses that define what happens kind of at a hemispheric level with our weather. Another way to think about that is this picture over here on the left is there's basically a 3-cell circulation. If you think about how air is transported from mid-latitudes, the equator, back around. So if you look closely at this is the Hadley cell, the Ferrel cell, and the polar cell. You don't need to know those. But what's cool about this model is this is generally what sets up the trade winds, the westerlies, the easterlies, like what controls prevailing weather. And a lot of it has to do with heat transfer from polar regions down to equatorial regions. So you can see down here in this cell, the closer to the surface, circulation is generally equatorward at the surface. Upper atmosphere, it is headed back up towards the upper atmosphere is headed up towards the north. You can see this one is actually, and this is the Hadley cell, or sorry, the Ferrel cell. This one is actually oriented the other way. So heat is transported at the surface, south to north, and upper atmosphere north to south. So you can see how that goes, and then you can see up there the polar regions back to the other way. So this, where we have intercontinental convergence zone, or equatorial convergence zones right here, a lot of what drives our westerlies is because of this circulation. A lot of what happens up at the poles is easterly component to weather. And that all kind of drives transport of energy, poleward to equatorward, really around the world.
What causes that shift in direction, bookended by the opposite direction, I guess? So.
Differential heating of the atmosphere as the Earth tips is some of it. Complex equations.
Well, in the picture, if I understand correctly, it's not really like the picture, because during seasonal variations, like one would be bigger than the other.
Absolutely.
Yeah.
Yep. The diagram on the right, I just liked it because I think one of the things that people sometimes struggle with is, what does high pressure and low pressure really mean? Well, of course, high pressure, I think Aviation Weather Handbook tells you that that is a clockwise flow and it's good weather and all that. But one of the key things about high pressure is that it's actually subsidence, which means air that is sinking down to the surface. So I liked this diagram because it shows it's cyclonic circulation, but it also shows anticyclonic, clockwise. And it's also showing the subsidence that happens there. And so this is what really, sinking air, drier process, fewer clouds, stable air. A low, counterclockwise circulation, convergence at the surface, upward vertical motion. And this is what really causes us to have weather associated with lows. So I like that diagram.
Yeah.
And you mentioned drier because it's air coming from the upper atmosphere?
No, as we know, as air rises, it cools and condenses. As air sinks, it's the reverse process, reverse adiabat process. So now when we start to put, and this was a AOPA, I stole a lot of things off the internet for this presentation so that I didn't have to draw on the board. You're all welcome. But this was actually a pretty good explanation that I found on the AOPA website, and hopefully I put them all in the right order. But if you have an area of high pressure, an area of low pressure, and of course the associated circulation with those, anytime you have a high pressure and a low pressure area, in between those, what are you going to have?
Wind,
And the wind is driven by?
the pressure gradient.
Yes, perfect. And so when you're looking at a map that has high and low, and of course they'll have the isobars on them, tighter together means what for winds?
Faster, higher.
Yep. What that really means is that there is a greater change, and think of these as like topography lines. And your lines are closer together, it's a steeper gradient, stronger winds. But what I liked about this was it actually framed up if you're relative to a high pressure area, low pressure area, what you can expect in terms of flying. So west of the high, because of the circulation that you can expect, you're going to have warmer temperatures generally because it's going to be a southerly component to that wind, and it's probably going to be pretty good flying. If you're in between, especially if the isobars are really closely packed, you probably are going to have a lot of wind. You might also have some shearing conditions as you start to have different winds coming around those two different circulations in different ways. So definitely something you want to think about. And then of course, east of a low, because of where you'd expect to have warm front, cold front draping behind it, you're probably going to have some pretty rough weather out ahead of it. Well, that was a nice little visualization of that.
Yeah.
Now, what I didn't go into today, and if we want to go into it, we can another day. I didn't do anything on cyclogenesis and what actually causes a low to form. If we want to do that, it's another day. I don't want to do it tonight, but happy to.
All right.
All right, so imagine we already have cyclogenesis happened. So we have a low that has formed, and of course we have fronts that have been associated with that. So simplest definition of a front, it's a boundary between two air masses. And you can identify that, and Eric, I think this goes a little bit to what the question was, but we know that we will see across that frontal boundary a change in temperature, a change in humidity, a change in wind direction, and a change in air density. So normally if you're looking at like a surface analysis and you actually have the little like station, it's basically like the METAR in visual format here, you can normally most easily discern where the front is based on wind direction. You'll see what direction the wind bars are. You can normally tell by temperature, especially across a cold front. Warm fronts are sometimes harder to tell. Occluded fronts are very hard to place based on surface observations at time. You normally have to place this based on satellite. Humidity, yes, you'll definitely see with both. Air density, you have to really look at the numbers closely, but you can normally see a pressure change across those as well. And then I found these really great kind of side-on profile of the 4 different kinds of fronts on Climb Aviation, actually. And what I liked about how they laid these out was one of the most important things about an approaching front is the vertical structure of it. So at the surface, where we experience the weather, you're like, cold front's coming, it's going to rain, and there's puffy clouds. But what's really important to note with cold front, and if I can go back to, I'll just do it from here. Cold air, more dense, always trying to wedge itself underneath warm air. Cold fronts always are very steep. They have a very sharp vertical profile to them. So it's definitely something important to note as pilots, because if you're going to choose to fly through a cold front, I don't know why you would, but if you chose to do that, you can get through it pretty quick. You just have to navigate that, which doesn't look like fun, as opposed to warm front, which we'll get to on the next slide. But if you're trying to look at the weather and say you are actually in the center of the country where you can actually very clearly normally tell where there are cold fronts and warm fronts, just even by looking at radar and satellite, but you also have really good continuity, especially out to the central US of observations weather reports, METARs, and all that. So you can actually figure out where's the front and how fast it's tracking if you're looking at that over time.
Beth, I remember you telling me once before, like, that the TAF should tell a story.
The TAF should tell a story.
Right.
Yeah, really good call out. So, and I wish that they would have, I was hoping that they would have it on this slide, but they don't. But for a cold front, of course, when do you expect precip with a cold front? Ahead, behind, with? Ahead of it, right? And for how long?
Till the front passes.
Yeah, but it's normally not too long, right? So cold front, they're normally moving pretty quick. 20, 25 miles per hour. Squall lines are more like 35 miles per hour. So squall line's going to be even out ahead of the cold front a lot of times. But you should be able to look and see showery precip, short duration, pretty intense normally to start. It won't start as like a minus RA. It should start either with a plus TSRA or with just a straight SHRA, SHRA. Should not be continuous rain. You should not see that if you're expecting cold frontal passage. Warm front, yes. Cold front, no. There'll also be things like the ceilings will probably drop for a little bit of time, pretty low, but then they'll come right back up. And then of course you'll see all the high pressure dip, and then pressure will start to come back up. And the biggest thing that you should be able to see with cold frontal passage is the wind shift. And it'll normally be pretty strong or just ahead of the front, strong for a bit after, but shifted more to the northwest, and then starting to tail off after. Winds behind a cold front can last for a bit, so that might actually last a little bit longer. And then you should also see and in the Air Force we had to do temperature in the TAF. Normal, I guess civilian TAFs don't have to have that, but you should see a drop in dew point after the cold front passes as well.
Cool.
Warm front. Warm front is basically an overrunning situation, and what overrunning means is you have cold air that's in place and the warm air is riding up over the top of it. Of course, the warm air is going to continue to rise up over the top of it. So one of the biggest indicators, and this is the one that a good forecaster will put in the TAF, but if you're expecting warm frontal passage, probably at least 6 hours ahead of a warm front, you should start to see a ceiling at 25,000 in the forecast. Because you have the cirrus and the cirrostratus and the altostratus that should be that precursor to the warm air or the warm front passage. Rain will start ahead of the surface passage of the front because it is falling through, of course, the colder air. So warm fronts can take 2, 3, 4 hours, depending on kind of what stage the cyclone is in, the upper level low is in, to actually get through. Ironically, given the name warm front, one of the most dangerous conditions for pilots that can exist with a warm front is when you have warm air and you have cold air or freezing temperatures at the surface. What's the result then?
It's super cool droplets.
Mm-hmm. Yeah, so warm fronts seem like they're benign and no big deal, but wintertime warm fronts are actually very dangerous. And again, same thing, like you should start to see the clues in the TAF several hours ahead of time for warm frontal passage. A lot of times they pass pretty quietly. Rain might continue, or you might have some low clouds for a while afterwards as well. A lot of times what you have to get is, even an area that has a warm front pass through will eventually have the cold front pass through as well. Those are some things you should look out for as well, because you could have actually quite a bit of weather happening over the course of, say, 18 to 24 hours if you get both warm and cold frontal passage. What was one other thing I was going to say? Good. Questions on that? All right, an occluded front. And this is actually not properly drawn because this part should be purple. But what happens with an occluded front is you have cold air, You have the warm front that has gone through, but then you have the cold front is actually traveling so quickly that it starts to basically outrun the pace of the warm front, and because it's cold air, it's going to wedge underneath. And so this is where you get this really chaotic kind of weather situation where you might have some rain for a little bit. That's what I was gonna say. Warm fronts are always rain, not showers. This, you might have rain for a little bit, and then you get something crazy like, and the winds will be picking up because this is normally when this upper level low is starting to deepen. So you're starting to get a lot more upward vertical motion with this, and you'll start to see wind speeds really pick up as a low starts to occlude. That said, it's kind of the beginning of the end. It's starting to run out of energy, but it could get a little intense for a bit. So tightening pressure gradient, you're going to have stronger winds at the surface. You start to get some of these crazy precipitation types. Do we know what this is?
Grapple.
Yes. Do you know what grapple is?
No.
It's kind of like little ice pellets.
Like hail, but it's like raindrops that freeze on the way down, or is it? Yeah.
Yep.
Huh.
Yeah.
Isn't there other types? Like there's grapple, hail, and then there's like a bunch of other.
There's also pellets are actually, I think, a type.
Yeah.
I don't have that book with me.
You a couple times, and I think we hear this from forecasters sometimes, like on the briefing and stuff.
Mm-hmm.
But can you define what you're saying by upper level low versus like
Yeah.
something else?
Yes. I sure can. So everything that you're seeing right here on this little map in the corner is happening at the surface. But everything that happens at the surface, weather is actually, I like to call it 4 dimensions because it's X, Y, Z, and it's also time. So there's a north-south, there's a vertical component, and then it's moving through time. So when you're thinking about what is happening with the weather, you have to think about it in that way. Every surface front, I'm gonna have to draw.
Damn it! No!
It's a trap.
It's a trap! This one right? Such a little marker. Is there an eraser? Alright.
For those of you tuning in, Beth is about to draw something on the board.
You're missing something crazy
That's
special right
just drew
now.
something that looks like a sea monkey.
Alright, so we got our low at the surface. They always have these crazy little things on them. Got our cold front trailing, we have our warm front out ahead. So this is what's happening at the surface. Then at 500 millibars, so 18,000 feet roughly, there is a whole another, so imagine this is our pressure surface at the surface. This is what is happening at the surface. If I go up to 500 millibars, most likely there is, this is a very aggressively drawn trough, but there is a trough of lower pressure at 500 millibars or lower heights. And this low pressure at the surface, of course, upward vertical motion, is supported by this 500 millibar trough. And it has to be from here up to where it is at 500 millibars, has to be what's called negatively tilted in order for everything to keep moving along the what's called the long wave pattern. The other thing that has to happen here, so this is at 500 millibars or 18,000 feet. Up here at 30,000 feet or 300 millibars, this is the jet stream. And what should be happening in the jet stream is something kind of like this as well, where there is a trough in the jet stream here. A lot of this has to do with transport of thermal energy and being able to support the continued divergence aloft to keep this low going. Now when a front starts to, or when a low starts to occlude like this, it means that this trough at 500 is starting to get vertically stacked, or maybe even getting out a little bit ahead of it, and at 300. So As long as you have this negative tilt from the surface back to 300 millibars, you'll continue to have a healthy low chugging along. As soon as those things start to catch up or even get out ahead of it, this starts to lose its upper level support and starts to die off. And then you have less temperature transport and cold fronts trailing become elongated and more of a stationary boundary. Does that help?
Yeah, it does. So you're drawing it in at least 3 dimensions there.
Yep.
Right?
Yep.
But when you're looking at 300 millibars, the way you've drawn it, are you drawing it kind of positionally there as well? Or is it like a slice of what 300 millibar trough might look like? So.
Can I? It'd take me a second to find what I'm looking for here, but how does this? Oh, it's the other way. Yours is backwards.
Yeah, I'm French.
There we go. All right. So this is 300 millibar heights and winds, where you see the shading, and basically you can draw the jet stream by following where those strongest winds are. So if I was going to be plotting if I was drawing the 300 millibar chart today for forecast purposes, I would draw the thing that you analyze on a 300 millibar chart is where is the jet stream. So I would place it here, here. There is starting to be a cut off. This is actually a really interesting feature when I was looking last night. This is starting to get cut off. So what that means, and this is also like starting to get a pretty big kink in it too. Eventually this will snap and it'll reorient itself here. But that's basically where I would draw the jet stream. Let's look at this spot right here, where it seems like we have a bit of a jet max of, how do I scroll down? So it's in the yellows, 140 knots. This time of year, that's actually pretty fast. That's something that you normally see more in wintertime, which is also why I thought that this feature was interesting, because also something that is normally more wintertime, but it is pretty far north. It's all the way up in, this is Hudson Bay. What is this sea? What's this called? This big body of water up here. I don't remember. Yeah, there you go. So this is, here's Maine. That jet max is right there off of like kind of the top of Maine. So that's what's happening at 300 millibars. This might not be the best example because this is kind of hard to do in a wintertime or a summertime pattern sometimes. But if I go down to 500, so now these things should start to line up a bit. So you can kind of see where the same long wave pattern is, and you see these little like short waves that are moving through it. This is a pretty good trough at 500, and you see where that jet max was at 300 millibars. There is also pretty strong, well again this is winds, but also we're starting to be just ahead of this this trough right here at 500 millibars. So pretty well lined up, a little bit ahead of it probably. And then if we go down to, let's see what's happening at the surface. We'll do this one. Low pressure at the surface, it's just ahead of it. So the one thing that I would say with this is where that cutoff low I think was starting to develop. That trough at 300 and 500 millibars was right about here. This is starting to kind of get out ahead of it on the front, but that low pressure area is right there. So they should stack up pretty well from 300 millibars, 500 millibars, all the way down to surface. Topography is probably messing with the placement of this just a little bit up here. But it looks like the computer model placed it pretty well. Does that make sense?
Yeah.
So when you're actually, if I was going to sit down and write a forecast for a given airfield, as I used to do, you start with, even if I'm forecasting for this little spot right here, you actually start your process all the way up at what is happening hemispherically and where are those troughs and ridges in the long wave pattern going all the way around the northern hemisphere. And then you look at that 300 millibar chart to figure out, okay, where are the jet maxes, what does it look like the jet stream is doing, and of course all of this you're looking at over time. And then at 500 you're looking for one, where the pressure differences and the pressure perturbations and the wind field there. You also are going to look at vorticity, which we'll get to in a second, because you want to know what the spin of the atmosphere is, most importantly at 500 millibars. Then you go down to 700 millibars to look for a low-level jet, important for moisture transport, but also for convection, and then on down through 850 into the surface. So you start big picture looking at all of these things and how they're stacking up, and then you start to get down to, okay, based on all of that, what can I expect to be happening right here at my location?
I see. So it's all, a lot of it is positionally vertically that's kind of driving your determination.
Absolutely. Yep.
Can I make an analogy about the cutoff low, and you can tell me if I'm totally wrong?
Yeah.
But like, when I think about, when I see that picture there, is I think about like when an airplane wing is at a high angle of attack, like this, and you start to have airflow separation, right? And
Yeah.
you'll have like momentary airflow separation, and then you'll have, reconnection. It'll go through these patterns of like turbulent flow.
Yep. Yeah.
I don't know if it's a good enough analogy or not.
It's a good lead-in because that's what starts to happen. And then what actually happens with the cutoff low, looks like we might surface. So what's really happening with the cutoff low, let's see, let me go back up to see if that one's actually cut off. So this low that was out here just to the north of Maine was still a low at the surface, and we still see a trough behind it that's able to support that at 500 millibars. What happens, and that trough is important because it is transporting energy north to south and feeding into vorticity and things that are in rotation that are going to continue to fuel the further surface development and surface deepening of that low. As a low starts to get cut off, what happens is rather than having this nice kind of flow, all of that energy starts to wrap around on itself. Once a low gets cut off at 500 millibars and becomes not cut off, but once it becomes a closed low at 500 millibars rather than a trough supporting a surface low, this is when a surface low starts to actually weaken.
Because it has nothing to feed it, right?
Yeah. The baroclinicity goes away.
So, okay, wait. This is up at a higher altitude, right?
Yep, this is at 18,000 feet.
So, because I'm trying to visualize in my head the 3 dimensions that's going on with that cutoff low. So, it's an air mass up at a higher altitude that's like the air under it has cut it off now. Am I thinking about that right, or is it?
Yeah, don't use the word air mass, but the flow through the atmosphere.
Okay.
Is it's basically making it so that rather than continuing to flow, it's just getting kind of stuck right there.
Okay.
It's kind of like when water's flowing down the river and then there's like the little eddy on the side,
Oh, okay. Yeah.
and eventually that it's not really flowing anywhere, it just kind of gets stuck.
Mm-hmm.
Anything else?
I'm sorry.
I don't mind.
No, it's good because I don't think any of, like, most pilots don't think 3-dimensionally enough about the atmosphere.
Yes.
I'm not flying at 30,000 feet is what I like there.
Not yet. Oh, scrolls the wrong way. Go back to slideshow. All right. And then the stationary boundary. So this was actually what Climb had for the stationary boundary picture. It's okay. Like, I mean, basically, this is exactly what you would see at the surface, but it's not really moving left or right. Stationary boundaries, one of the characteristics of them is that they don't move more than 5 miles per hour. That's kind of the rule of thumb. A stationary boundary is not going to move more than 5 miles per hour. That is happening because, and this is, I found this on Penn State's website, really good, like, Meteorology 101 class, all fully available and accessible on Penn State.
Free?
For free.
Wow.
Yeah, it's really good. If you think Penn State's a good school. There are better meteorology schools out there. Actually, Penn State, Texas A&M, and of course the Air Force Academy are all great.
Plug.
Shameless plug. But what I liked about this was, because I think Sophia was like, how do you actually tell, like, what's happening with the air masses? Because you're used to, if you're seeing a cold front moving, you're seeing like a dome of cold air trying to wedge itself underneath warm air, and it's just going to keep pushing. But if the general flow is these two highs that are kind of stalled out, continental polar and maritime tropical, and there's not really anything that's moving them along, you get the stationary boundary that sets up. And I thought this really showed why that happens. There's no, normally behind a cold front you'd have that northwesterly push, but just the orientation of those, they're basically at opposing flow lines at the surface. Kind of get stuck. And it's going to take either some sort of upper level perturbation that causes a low to jet up on here and start to kick some energy along and shift the wind a little bit, or it just stays there. Sometimes high pressure can build, something might make this slide a little bit, and then you start to get a little bit of movement, so you start to have actually a cold front and a warm front again, but those can set up for a long time. Side story. I think I was in middle school, and there was a high that had set up like that. We'd had snow. This is March. We'd had snow. It was Iowa. It was in the 50s. So the snow had all melted. We had 32 straight days of not seeing the sun because we were basically stuck under a stationary boundary like that. Mm-hmm. And so it was raining a little bit, but not a lot. It wasn't like river flooding, but it got to the point where, of course, I lived out in the country on a gravel road, and they had to put a bus embargo in place. So if you were a school kid that needed to ride the bus to get to school and you lived on a gravel road, you had to find a different way to get down the road. That went on for like 2 weeks, I think, that the bus embargo was in place. So it was just wet and nothing happening. And eventually, the high, I think this high down to the southeast retreated. The high moved in, kind of just built, so like we just started to have like sunnier days, and things eventually dried out, but it wasn't like there was some big kicker that moved the stationary boundary out of our way.
So when you get a cold front that goes over the top of a warm front, is that when you get the tornadoes? Like is that the warm air that's rising up through and disrupting and creating destabilization?
We'll talk about tornadoes in a second.
So I really like the image on the right that you pulled up there. I think part of the problem in teaching this with students sometimes is the names of the fronts themselves, like stationary, okay, I get that. Cold, okay. Warm, but I think what's hard to understand is that and you laid this out earlier on, is there's much more that defines, the front, than just
this part?
Yeah, just the one thing, right? Mm-hmm. So it's all of these things which are leading to the definition of this front. And I think, when people first approach this material, they're, in aviation at least, they're confronted cold, all right? Cold, all right? I'm trying to wrap my head around why this is happening, right? Just cold air. There's more to it, right?
Mm-hmm.
So I think that's where a lot of the confusion comes from when I try to explain this to people or people read about it. It seems like it's overly simplistic terminology.
For a very complex process.
Yeah.
Yes.
Because there's a lot more going on. And when you try to build your concept around cold or warm, like it doesn't always work.
Mm-hmm.
And I think with the stationary front, that's part of what the big, like it becomes evident in the problem. The problem becomes evident because you've thought about a cold front, you've thought about a warm front, and now you're seeing them like this, and you're thinking, wait a minute, like why is it driving this weather or precipitation?
Mm-hmm.
So are the stationary fronts always sandwiched between high pressure systems, or is it possible to have?
They're going to be. A stationary boundary is a dividing line between two air masses.
Yeah.
So yeah, generally you're going to see high pressure and clockwise flow around a high. So
Okay.
yeah.
So there's no other circumstance where it would potentially form, I guess.
No.
All right.
Well, you wouldn't see it between two low fronts or low pressure zones or masses.
Yeah.
That'd be a bad day.
Yeah.
That's read the book The Perfect Storm. That's what happened.
Let's go back.
So I saw the movie on.
Yeah.
They made a book out of it.
They made a book out of the movie.
Well, they do that. It's not like that's unheard of.
Remember Airheads? Copy of the movie Airheads, the stupid movie from like the 80s and 90s.
Oh, really? They made a book out of that?
Where he wants a copy of Moby Dick, and like, the movie or the book? He's like, they made a book out of that?
All right, this was not explicitly on the list, I don't think, but when Eric called me to plant the seed for doing this tonight, it seemed like one of the questions that came up was the difference between convection and vorticity. So I just wanted to make sure that was clear for everybody. I couldn't find an image that I loved for this, but this gets pretty close. It doesn't have advection on it, which is really important, especially around here, because advection is what causes the marine layer to come in overland for us. But heat transfer processes, there's radiation, such as the sun heating the surface. Conduction, which is the transfer of heat from a surface to whatever's in contact immediately with it. And there's convection, which is vertical heat transfer, so warm air rising, as the picture shows. Of course, around here, conduction for us also happens in the form of the cold ocean cooling the warmer air that's right above it, which causes an inversion, but also causes our marine layer. So we'll get to that in a little bit as well. But just want to make sure this was clear. Convection is what gives us clouds, precipitation. Of course, strong convection gives us thunderstorms. Vorticity is actually just, it's not a heat transfer process. It is a measure of the rotation of fluid. So think of the atmosphere as a big fluid. Fluid dynamics are really what drives what causes, what moves the atmosphere. Vorticity is the measure of rotation within that fluid. Vorticity advection then is the horizontal movement of that rotating parcel of air within the atmosphere, normally driven by wind. Positive vorticity advection, or PVA as it's called by people in the know.
Right.
Cool people who spent way too much on big, thick textbooks like that. That is cyclonic rotation being transported into a region, and there's a picture on the next slide that'll help to hopefully clarify a little bit of what's happening here. But positive vorticity advection also, because you have a rotating parcel, and then you're as it continues to rotate cyclonically, it actually is inclined to upward motion. Negative vorticity advection is the opposite of that. So the impacts down there at the bottom, of course, with kind of what we just talked about here, like how does that low actually develop? And remember the 500 millibar trough up above supporting that surface low. 500 millibars is where you look for vorticity and vorticity advection in the atmosphere. So if you start to see positive vorticity, which you'll often see coming out of the base of a trough up there at 500 millibars, that will further intensify that surface low because that rotation and that parcel of air is creating more upward motion. Vorticity lobes, as they're called, or an area of positive vorticity advection in particular, moving through at 300 millibars, the base of a trough at 300 millibars, which is going to be where the jet stream is. If you put more energy into the base of that trough, you actually create a faster flow coming out of it. So you get a what's known as a jet streak, which is also a good ingredient for a low at the surface to deepen just how everything stacks up and you're able to have more upward vertical motion.
Interesting.
So in the form of a picture, because we're going to talk about tornadoes a little bit later, and also because we're pilots, and I thought that this was kind of an important one to think about. If you think about wind shear, that is actually horizontal vorticity because the winds are blowing 20 knots at the surface, but then at 850 millibars, which is about 5,000 feet, it's 30 knots. You might not notice that too much, but if you start to have, it's calm down here at the surface, and sometimes with even the inversion here, you could have 40 or 50 knots up at 5,000 feet pretty easily. You're probably going to notice that at some point. It's going to cause, kind of like when we talked about wingtip vortices. This is like the atmosphere putting out a wingtip vortice. You can also have it directionally, which is actually very common with inversions, where down at the surface, winds might be calm, or maybe even for us, we get a little bit of like onshore in the morning, but then up at 700 millibars, you might have some sort of crazy offshore kind of flow depending on where prevailing high is around us, and a pretty significant wind shift up at altitude when you're flying along. So horizontal vorticity is an important one, and we'll come back to it when we get to tornadoes. But so that's horizontal vorticity. This is more of what is causing intensification of surface features. When we think about lows that are starting to form and to deepen, and it most of the time, if like meteorologists are going to look at 500 millibars to see where there's vorticity advection, and they're looking for when is some sort of rotation moving through this pattern. And if there is, that rotation is often going to turn counterclockwise here. It's going to cause rapid deepening of a surface low, because that counterclockwise circulation and the upward vertical motion associated with it, of course, causes the low to continue to deepen. So vorticity is like big picture influence on upward vertical motion in the atmosphere. Like 500 millibars, thinking about supporting frontal boundaries, cyclones, big areas of low pressure. Whereas convection is going to be more of a micro scale process that will feed into afternoon thunderstorm development, land breeze, sea breeze kind of situation, convergence and outflow boundaries that cause lift and convection. That's where, does that help to clarify the difference between, they're both lifting processes, but one is smaller scale and heat driven. This is fluid dynamic rotation and bigger scale, supporting bigger scale features.
And when you were saying the low deepening, what do you mean by that?
Good question. So the surface, the low is, say it's 1,003 millibars. And if you increase the upward vertical motion around that low will then, you have If you have upward vertical motion, there's lower pressure coming in at the surface because it's all getting sent upwards. So 1,003 millibars might drop to like 990 millibars.
Okay.
That's like, sorry to be hurricane level kind of numbers, but.
So the easiest way to see vorticity is to see satellite imagery and winds. Like,
Yeah, if I was going to go back over here again, there should be an upper level dynamics, 500 millibar vorticity. So if we remember back to where our low was up here in over Maine, you can see there's so the lines are of course the 500 millibar heights, but the colors are the relative vorticity, and so there's a little bit of vorticity there, so you'd expect to see continued upward motion there. Well, that's the kind of thing that you're looking for. A water vapor satellite image is where you're normally going to see this kind of feature if you wanted to actually verify what you're seeing here to a real tangible product.
and that's because you're seeing the change in the adiabatic or a change in the moisture.
Yep.
Yeah.
Yeah, exactly. Likely a dark streak just behind a. Okay, do they have? Yeah, you have to pay to get satellite on this website. But yeah, you'd see it. There's always that kind of like dark. It's drier intrusion is what it's called, but that dark area on a water vapor image just behind the low is what's going to give you the clue that there's something happening there.
I think what's interesting about like showing all these different images sometimes is like we're talking about weather, but we're looking at it from pressure, temperature, vorticity, water vapor, like we're looking at all these different things, but it's all just like putting on different sunglasses and looking at an elephant, kind of.
Well, the other thing that's important to anytime you're looking at or you're trying to put together a forecast, you should never look at a point in time. You should look at what the trend is over time. Is it getting worse? Is it getting better? Am I high or low? It's kind of the same thing here. Like, is it going to get worse? Is it going to get better? Is it going to stay the same? And that's where you have to look at everything all stacked up together to see, like, is the 300 millibar trough trending ahead of the 500 millibar trough? Is the low starting to close off at 500 millibars? Like, those are the things you have to look at.
I assume they can overlay those? Like, you can overlay the...
No. You have multiple windows open and you kind of just...
Oh, your eyeball?
You also, yeah. But if you're doing it a lot, you get used to what you're looking at.
Yeah, because it seems like you drove home the importance of it. You would think that there'd be...
You would think. You would think.
On the vorticity tube thing, like there's a group of people that are trying to build very lightweight gliders with high glide ratio that are, the whole theory is that they might be able to go super long distance actually flying along a vorticity tube.
Oh. Kind of like a surfer. Like you're just trying to stay on the wave.
Yeah. And there's
very specific places in the world where you could do that.
Yeah.
Yeah.
Very specific places.
That's cool.
Yeah, well, it's interesting, but it's like this whole idea of getting up close to the jet stream and
Yeah. All right, how are we feeling?
Good.
pretty good.
I love all this information.
Nope. Slideshow. Marine layer. Wish that was my photo. It's not. Okay. Apparently, in San Francisco, they call it Carl. Why won't Carl leave? One of the best resources.
Wait, what? In San Francisco, they call it Carl?
Yeah, the fog is called Carl.
That's funny.
Yeah, there's like all kinds of like blogs and like there's a Twitter account. Yeah, it's known as Carl.
I call it the cloud of doom here.
I don't know why we don't call it Carl down here.
Yeah.
But yeah, they do.
Is that because of Carl's band?
No. But
Just let that
Yeah,
one.
okay.
Alright, let's just let Sean sit down for a minute.
They all can be winners.
a really handy, some of the most actually helpful weather sites, or trying to figure out what's happening with our local weather around here are people who kiteboard or do like, whatever that's called, where you're sailing out on kite sailing.
Do you mean when you're out on the ocean with like
Yes,
the
that. Those guys are very tuned into what's happening, one in the ocean and two in the air immediately above it. So, and they nerd out in a big way on it. But you can actually learn quite a bit from some of those sites. So like the Weather Flow blog is one of those. This Weather Flow has one that's focused on the West Coast, but it's also international. So if you wanted to see what was happening in other parts of the world and how the East Coast is a completely different situation because they have the Gulf Stream, which is a warm current, and so that's what's driving their coastal ocean influence. Of course, we have the California current that is frigid, and what doesn't help us in the summertime is this North Pacific high sets up, and so as the air rotates around that high, you would think like, hey, it's summertime, it's going to start warming up. Well, what this high actually does is it continues to pull cold air all the way down from the Gulf of Alaska, and so here along the central coast and down into California, the surface starts to warm up, but then the North Pacific high causes a southerly flow. So the water warms up, but it continues to move south, and we just get upwelling that happens here. So our water stays pretty cold all the way through the summer, driven by the North Pacific high. And of course, there's a big area of high pressure over the Great Basin. In between, you get the southwest monsoon, high base thunderstorms. So the marine layer is the forecast products, and the explanation of what's happening in Southern California is light years ahead of what they communicate here in the San Francisco Bay Area. So if you follow along on the Oxnard National Weather Service site, they have all kinds of really cool graphics that help you understand, like, hey, it's cloudy again, why is it happening? And I thought this was a really good one. This was June 27, 28 of, I think, it was a couple years ago. This wasn't this year, but very well could have been this year. But it shows you what's happening with that deep marine layer, and we'll get to the difference between a deep and a shallow marine layer on the next slide. But basically, anytime a low or a trough comes over, or the high starts to retreat a little bit, that's actually bad news for us trying to fly, because that means that the marine layer is getting deeper. And a deeper marine layer means that inversion actually lifts up a little bit, which allows more of the cloud layer to develop and to move further inland. So a lot of times, like, if there's good high pressure here, it's going to help to keep that inversion down. It's going to keep the low clouds closer to the surface, and most of the low clouds are going to be immediately at the coast. But as you start to have a little bit of low pressure, it allows that marine layer to deepen and expand, and it also gives it more and an ability to move inland as well.
So this is kind of what causes the quote unquote June gloom.
Nailed it. That's not on. Oh, it's not on this slide. I thought it was.
So is that why here, every single morning pretty much I wake up in Marina, it's like fog right there. And then when I drive over here, even if it's an overcast day, I can almost see it like tapering up sometimes.
Yep.
Is it the same process?
Exactly the same process.
Okay.
Exactly why I use this slide. This is the exact same thing that's happening out right there, right now. So of course, as the sun actually comes up and starts to warm up these inland areas, it helps to push some of that back out, and of course you just get dissipation of clouds. They start to burn off with the sun coming in, but this is the exact same process that happens here.
So is this more convective, or is this more vorticizal?
This is more advection.
Advection.
Yeah. So you have the cold ocean surface, the warm air above it, when that causes the inversion, but also it causes the clouds to form. And then it's that differential.
That's not advection? That's not advection?
Yeah, it's advection.
It's
So advection is then, so it's conduction first, and then it's advection that actually transports inland, because there's a difference in temperature over the ocean versus land, and so it wants to move this way.
And so to summarize that last slide, just real quick.
Oh, the other one,
Yeah.
the heat transfer
No,
one.
the one worth the, that one.
Yeah.
This is a trough of a low pressure weakens the subsidence, which weakens the inversion. So
Subsidence.
yeah, subsidence.
Yep.
So the trough weakens, the inversion, or the weakens, and it allows it to
That's kind of funky wording.
ascend.
Yeah, so subsidence is always associated with, of course, sinking air. Normally that's high pressure pushing down is what causes subsidence. Low pressure is normally associated with more of a rising upward motion of upward vertical motion is associated with the low.
So
Downward
the
vertical
low
motion.
pressure strengthens.
Yeah, so the low pressure is weakening the subsidence. I would actually say that it's not weakening the subsidence. Subsidence stops if there's low pressure, because now you have an upward motion instead of a
Well, when I was
downward
reading that
motion.
again and again, I was like, I think that's probably not worded.
That's
the best
not
way.
worded well at all.
So
I just looked at the picture. I didn't read the words.
yeah.
What words?
So low pressure weakens the substance is the same as low pressure strengthens. Yeah.
Low pressure is driving
Yeah.
upward motion that is deepening that, or causing the inversion to come up a bit.
kind of relieving that pressure.
Yeah, exactly.
Yeah.
To drive upwards.
Yep. I think the next slide actually does a pretty good job. Now I'm all worried. Like, what do the words say? I didn't read it. The picture looked cool. I don't have to draw on the board. But yeah, the top one is right. So if you have strong high pressure aloft, high pressure causes subsidence, which is sinking air. And the stronger that high pressure is, the shallower that marine layer is going to be, because it's pushing down on that inversion. It's just not giving a lot of space to let those clouds actually develop underneath it. You always know the top of the inversion, and you guys have probably felt this when you've been flying. Like if the marine layer is in and you pop out through there, it'll probably immediately warm up at least 10 degrees and start to feel a little bit different. If there is weaker high pressure, then there's still a subsidence that's causing, it's still holding that that inversion down and still compressing the clouds a bit, but there starts to be a little bit of an intrusion because it's not as strong. So it's starting to come inland after that. And if there's low pressure, of course, that gives a lot of room for those clouds to expand, because you're going to continue to have, because of the surface of the ocean continues to stay cold with the upwelling that's happening, you continue to have warm water over the top, but now you have low pressure, so you still have the conduction happening in that boundary layer, but now you have a little bit more room for those clouds to rise up. The inversion is still going to keep it from going into any sort of convective type cloud, but you do see the clouds start to come in a bit more.
Something that's kind of tripping me up here is the temperatures, right? It's almost as if, I guess in my mind, the gradient of the temperature, like the greater the gradient of the temperature, I would think the more that fog would want to come rushing in.
Yeah.
But it seems like in this, like the bottom one with the low pressure aloft, the temperature gradient's actually less. And that's
But part of that's because this has allowed the temperature inversion to come up to here instead of keeping it down here. So that colder air that's kind of trapped underneath that inversion stays here. And also then you just have the influence of the clouds not allowing it to heat up as quickly as open sun.
right, but then I'm thinking about the high pressure being cooler air, right? So I would think in my mind that it's
Don't think of high pressure necessarily as cooler air.
okay.
Think of it as drier air, sinking air. but not necessarily cooler.
Okay.
But that in the
And-
summertime, you've got conduction that's fighting for the surface is warming up, right, as well. So that's gonna
Yep.
drive your lower altitude temperatures up.
Mm-hmm. The other thing that's interesting that they don't really, it's kind of a different concept, I guess, than what is here, but the other thing that can happen is if wind starts to come offshore, a downsloping wind is a drying wind and a warming wind normally. And so if we start to have pretty strong offshore flow, that will burn all of this back to the coast pretty quickly, and you won't have any, like, that's what happens a lot of times here in August and September when we have nice flowing weather. It's because the flow's gone offshore.
When you get that high pressure in the Great Basin,
Yeah.
it drives all that air out.
Yeah, the Pacific high starts to retreat just a little bit back to, it actually slides south a little bit, and the Great Basin high builds in, and we get more offshore flow.
I mean, there's a lot more that goes into whether the fog's going to be there or not, right? I mean, this is all about just how deep is it going to go?
Yeah, there's a I don't know if I can find it.
But
Oh, is it this one? Yes. So, when I talked about forecast funnel, this is actually essentially a forecast funnel for determining at SFO if you're going to have, this is a like flight category, any significant weather, wind, low level wind shear. So this is basically what the, this is on the Oakland Center's website. There's actually a really great, Oakland Center actually does a weather briefing for, like it's a shift change briefing for weather for controllers for all of Oakland Center. It's pretty handy if you're not quite sure what the weather's going to be doing. They'll sometimes touch on Monterey. Of course, they spend a lot of time talking about SFO, Oakland, and San Jose. But this is what a forecaster is going to go through and look at to figure out how to build out this particular table, and then that gets translated into a TAF. So they look at things like, there's a map that has all of the, of course, you guys are familiar with those, all the different sensors in their reporting. This is the SFO METAR for, I think they go back 18 hours normally. Might even go back further. They're looking at winds aloft. They're looking at just what the, this is an automated forecast that gets spit out. Of course, any potential hazards in the area. The one I wanted to get to is this. So one of the big things that they look at is the pressure, 24-hour pressure changes and the temperature and dew point gradients between different places kind of along the, between SFO and other places. So how much is the, which ones are these? These are, yeah, these are pressure differences. So what is the pressure gradient between, I don't know where ACV is. Vacaville. And they actually will reference a couple of these from time to time in the forecast discussion, if you guys read that on a regular basis. And they should have rules of thumb that they're looking at that determine if I'm seeing a pressure gradient of X amount between these two locations over this amount of time, then that probably means that the inversion is as strong, and I'm going to need to forecast ceilings down to like IFR. I don't know what their rules of thumb are, and I haven't spent enough time looking at this to know how they're influencing it, but that's the kind of thing that they're looking at. And then, so that's 24-hour changes in the gradient, and then those are actually the forecast gradients.
That's interesting. So it's like, they must have a rule of thumb for like,
Yeah.
if the pressure is this much between here and there, it's probably gonna.
Yep. Yeah, but these are all the things that they're looking at. Like this is actually a really good, like what's the 24-hour temperature change and the 24-hour relative humidity change in the area. Which is an interesting one. And then of course, it always helps to look at what's really happening. So look at that. Webcams are handy, other links. So that's just for doing a ceiling and visibility forecast. That's the level of detail that they're having to go to figure out what might be going on.
Wow, that's a lot.
So it's really hard to forecast.
Yeah, exactly.
So I guess we gotta give them a little slack.
Yeah, just a little.
Only a little. Is that helpful?
Yeah.
Yeah.
Cool. Now the fun stuff. Made our signatures. This was last night. But what I wanted to highlight was, one, refresher. We'll leave shear off to the side for a little bit, but of course we all know to have a thunderstorm you have to have lift, instability, and moisture. Shear is what will actually help to, like it says, maintain or organize storm activity. So lift, instability, and moisture can all cause maybe a singular cell. As you start to introduce shear into a convective environment, that's when things really start to have a life of their own. So Sean, I didn't know if you wanted to look at like kind of what are common features or common signatures that you might see on radar. We'll get to tornadoes specifically in a second because I know that was one of your questions, but these are things that if you're anywhere else in the country besides here on the very boring West Coast, things you need to watch out for, make sure your students are aware of as they're thinking about flying. You might think like, oh, hey, this is a squall line. Like I said earlier, squall lines move at like 35 miles per hour. They have a lot of energy. I can scoot through there. Don't. It's a bad idea. That's what squall line looks like. Very narrow, like that's probably only maybe 15 miles across. Very intense through there. Bow echo, and a lot of times you'll see this form on a squall line. With a bow echo, and this is more of something you want to be aware of at the surface because again, you should not be flying a plane through this. But if it's easier to see a bow echo, and anything you're looking at on radar, you should be really looking at in motion rather than a static image. But a bow echo is, I mean, you can see the line is basically starting to make, and this isn't a really pronounced one, but it's starting to make a bow. It looks like what an archer would shoot. The thing that you have to be most concerned with here is if your plane is here and not tied down, it's about to blow away because surface winds with a bow echo, I mean, a line like that, I would be issuing the 50 knot wind warning for that. So, something to keep an eye on there.
And that's still moving at around 30 knots, or is that going to be progressing faster?
Still probably about 35, maybe a little faster. Yeah, I mean, the part where it's bowing out is going to be moving a little faster anyway. So, yeah. The other thing that will often happen is that bow line or that bow echo starts to push out the surface winds out ahead of it. Because a lot of times you'll start to feel the gust front out here. This blue actually might not be precipitation. That might actually be dust getting kicked up from the kind of outflow from that. But if you have another line out here, depending on where this one formed, or maybe like one of these cells collapses and you have this, these two things are going to come together, and convergence at the surface means pretty explosive convection, which we'll see in a second. This is what you're wanting to see. So this is actually very rich. There are 3 tornadoes potentially on this image, but the thing that's indicative of a hook echo, and a hook echo is normally indicative, like if you're sitting at the forecast desk and you see this, you are immediately issuing a tornado warning. Even if it's not confirmed on the ground, that is pretty telltale sign that that's what's happening. So supercell here, and of course I don't have the satellite image to go with it, but you can expect this to be pretty, probably 50,000 foot cloud tops for this one. And what you start to see is it's always on the rear flank downdraft. So they're always on the back side, and you'll start to see this start to hook around. So there's probably rain, hail, all that kind of stuff happening out here. There's going to be some more rain back here. And this is you have to have a little bit of dry air intrusion, and that starts to wrap in, and that actually helps to strengthen the tornado, or strengthen the rotation in the mesocyclone that then the tornado comes out of.
Now this is happening during a low pressure or high pressure system?
Depends.
Okay.
A lot of times in the summertime, if you have instability, moisture, and lift, you can have thunderstorms under high pressure. So like the southeastern U.S., it's not necessarily frontal. The lifting mechanism is not frontal. It can be daytime heating. It can be orographics, like mountains can cause it sometimes. That's why we get thunderstorms in the mountains in the afternoon. And a big thing that will cause convection in the southeast in the summertime is just it's so hot, it's so moist, and you get a little bit of dry air that comes like kind of across Texas called the dry line, and that interacts with that warm moist air kind of from the Gulf. And I think this is in Oklahoma. This is often the result.
Wow.
Do they always track southwest to northeast, or is that an old wives' tale?
Generally, yes. A bit of a wives' tale because they can't go the other way.
Generally, yes.
But generally, yes.
The other way.
Generally, yes. Generally, yes. My dad always stood on the south side of our house to like watch to make sure that the tornado wasn't going to get us. I only saw one once. Yeah, they normally go southwest to northeast. The one that was, and this is what was interesting, because it sounds like you guys looked at that derecho that happened in Des Moines area on Monday night. There was so derecho is a little bit of a different situation. It's a long-lasting wind event, convective wind event. It's normally straight-line winds, but there was actually a tornado that formed in that. It didn't form through this normal process. And so the tornado actually, touched down in Des Moines, which hasn't ever happened. There's never been one in the city. And it tracked kind of southeast to northwest instead of, Yeah, I went the other way. It was interesting. I can't remember what I was going to say about this, but this is how a tornado happens. I actually like the next graphic that I have a little bit better. Because it's very busy, but it also shows, what I like about this one is it shows you like Virga. What's Virga?
Rain that doesn't meet the ground.
Good. So of course there's Virga out ahead of it, light rain, moderate rain coming in here. The forward flank gust front is going to be a thing that happens because of the forward flank downdraft. So of course the air is coming up into this giant cumulonimbus cloud. It has some spin to it, and then as it circulates down through here, there's always a forward downdraft. And it often at the surface will seem like there's some sort of cold front, not a cold front, but a definitely cooler temperatures and drier just because of how it's come down quickly, and as it has come down through the atmosphere, it's dried out a little bit. So that also sometimes causes this to be Virga more so than rain. The other thing that's interesting, if we think about vorticity, one of the characteristics of supercell development is that you have to have a low-level jet a lot of times. So low-level jet is going to be a wind at least 35 knots, and it's going to have pretty much a south to southeasterly component to it. And so that is going to be feeding warm air in here. And so for supercell development, that is one of the key signatures. If you see that in the morning when you're doing your morning forecast and building everything out, and you see there's going to be a streak of, it's at 925 millibars normally, that kind of energy coming in here, you need to start thinking about putting out a tornado watch most likely for the afternoon. The other thing that will then happen is a lot of times we have fluids coming in from the more from the west or northwest. And so then you start to have strong wind coming in here at 925 millibars, so just above the surface basically. And then at 700 millibars, you get more of a westerly component. So now you start to have the vorticity situation. You start to have a rotating parcel of air. It rotates along the ground, but as it because of this low level jet and what's happening here. But as it starts to get closer to where there is this convection, that rotating parcel of air on the ground starts to get spun vertically and forms a mesocyclone. Mesocyclone gets wound up tight enough, it will throw a tornado out the backside. That's a very simplified version. Explanation.
So they always go ground up then to.
That's a very good question.
So like that one, we saw that,
Mm-hmm.
and then walked around the building, and I was like, oh yeah, never mind, it's a real tornado. When he walked around that.
Yeah, it's a lot of times.
But it wasn't. It was like you couldn't see it at first, but we saw the funnel,
Mhm.
and then it. But it also, it wasn't until it started picking up fallow ground
Yeah,
that it.
it's a little bit of a misnomer because
Yeah.
a lot of people think like the tornado comes out of the sky, and people are like, no, it can't come out of the sky. It has to come up from the ground.
But like the weather wasn't really like that radical, so it was
Yeah.
kind of like, wait, so if you were out flying, that was just south of Greeley. So if you're out flying, like it wasn't like there was a lot of telling. Like I've seen way worse weather living in Oklahoma, Texas, Panhandle, Florida.
You should be doing this.
No. I don't know that much about it. That's why I'm fascinated by it. But then you see like the anomalies. It's like that one. I don't think you would have batted an eye of really going down. They had like a kind of high level cloud that wasn't real convective. But that was the day that when it started ripping right there.
Yeah.
So I don't know.
Did it last very long?
Went a few miles and it got. I was working on a feedlot and it got within about 500 yards or so of the southwestern pen. We were about ready to go. Start scooping cows up. I mean, there was nothing really you could do, but yeah, it went for long enough to do some damage across a couple of towns. But
The tornado that took out our neighbor's garage when I was growing up, you didn't see anything drop out of the sky. We were looking across, and our neighbors were like a quarter mile away, so it wasn't like it was like next door. But their garage, the shed that they had, kind of started to rotate, and then it started to just like rotate and lift it up a little bit, and then it just like splintered. And it kept going, but you never really saw, because I don't think there was enough like dust, and it had been raining a bit,
Yeah.
so that was kind of keeping the dust down. You didn't see something go all the way up to the cloud, but clearly there was rotation that was going all the way down to the surface.
yeah, awesome is an understatement. We had one at 10:30 at night in Oklahoma at Vance Air Force Base. Actually,
Mhm.
we were on base there,
Mm-hmm.
and it went from kind of wild weather to just all of a sudden trees started flying by, and then when the lightning struck, and you could see the swirl right in front of us, and it was just like everybody dived inside. But then it picked up, went over town, and then dropped down on the other side of town, and then went down again. But you could just see it, and then it was clear skies, calm winds.
Mhm.
Wow.
Yeah.
But it's like it had a life of its own, as it was. They're fascinating. When you find faith in a higher power, I mean, it's just like it's an amazing amount of energy. It's so they can be so localized too. It's
Mhm.
incredible thing to see.
Yeah, and it's interesting, the precipitation is always ahead of a tornado. So normally, after the tornado goes through, it's done raining.
It's like the birds come back out
Yep.
again.
So
and
if it's
stuff.
raining and you see a tornado, run.
It's generally a good life rule anyway.
Well, but if it's dry and you see a tornado, you're probably on the backside of it then, maybe.
Oh, yeah, sure. Give it a try.
Okay. We had one tornado when I was a kid in
Where was that?
Los Altos, just up in the Bay Area. It was during that El Nino back in like '94, and it was just the wildest thing. I remember playing basketball in my front yard and just watching the clouds, like just going like I've never seen that before. And then just all of a sudden it just went. And
Like a water spout type deal, like okay.
it was on the ground, and it went through actually my middle school, and there was like some people playing tennis, lifted them up, slammed them across the tennis courts, and like they went and hit the fencing, but like I think it only lasted for maybe a good 2 or 3 minutes, but it did some damage, and it was like one of the first tornadoes that they, recorded in the Bay Area. It was wild.
In my entire life, I think I've seen 2 in Monterey County. There was one I saw, was really young, like kind of just past North Salinas here. It was very interesting. It was very small.
Yeah.
It didn't last very long. Not like, didn't seem like we have a life of its own. It didn't do any devastation or destruction, but it made contact with the ground.
Still enough to jack you out. Probably more so if you're not ready for it.
Right. And you never seen one before. I'm not used to it.
Seen a water spout out here once, out on the bay. And it died before. It kind of just hung out there for a bit. Didn't really move anywhere, but it was out there.
In the convergence zone over by Hollister in the afternoon, you'll just, when that starts coming in, you'll see just dust devils all over the place, start popping up. Like you're in the pattern, you start seeing dust devils kind of coming towards the airport, and you're like, it's gonna get interesting.
Maybe it's time to go on a different airport.
Yeah.
Alright, do you guys want to look at real weather, or are we done?
Real weather.
Can I ask about what's like a haboob? Is it just like a?
Oh no, I never deployed.
Huh?
I never deployed, so I never had to forecast a haboob. Yeah,
They
it's
have, like,
basically,
Arizona.
yeah, they have in Arizona. It's
Oklahoma. Big old dust storms.
It's basically the reason why I saved this last night, because I was trying to figure out, I look at radar and satellite on my phone, and I was like, I don't know what website to go to. I was looking for websites to use, and of course these are good ones, but this was actually very interesting. So this is what do they call this? Geocolor composite. So they try to figure out how to replicate a visible satellite at night using color to do it. But what's super interesting is this thunderstorm here, and I went and looked at Lamar, which is right about here, and La Junta, that's a little bit to the west of that. And obviously this blew up, but you can see the outflow. So there was something else that was there before. And so I went and looked at the weather when this was happening, and both of those places were gusting 35 knots at 10 p.m. So yeah, that's what can happen when a thunderstorm collapses. Now, likely what happened was, it looked like there was one back here and another one here. There was probably 2 outflow boundaries that came together and caused this one to come up. Normally, nighttime convection is a result of surface convergence from outflow boundaries. But there was a good chance, I didn't keep watching, I went to bed. If this kept going and this was something down here, that could have come together and caused something to happen further into Oklahoma.
So that lighter, almost bluish one, was that at a higher or lower altitude?
Lower.
Okay, gotcha.
It's at the surface.
Wow. What causes the, you go to Florida or New Orleans, Mexico area, the 4 o'clock, on schedule, thunderstorms that happen all the time over there? Why is that clockwork almost?
It has
Going east.
Build, and then it bursts.
dry line would be back here.
Yeah,
So
but
that's
doesn't
what-
it move east in the afternoon?
Florida panhandle's a different thing.
Right.
Thunderstorms here, yes. When I was stationed at Barksdale, we did the area of responsibility for Barksdale was Kansas, south and east. Any Air Force or Army base in the southeastern U.S. we were responsible for. So dry line was something that sets up in Texas in the summertime, and it will, if it propagates a little bit to the east and it interacts with Gulf moisture that's coming up here,
Right.
that'll trigger thunderstorms down there every day. Florida's a different situation. It's purely based on land breeze, sea breeze interaction. So land heats up in the afternoon. There's moisture that's coming on flow, comes up, makes thunderstorms, they move off, and the reverse happens at night.
So it's just a really more intense advection
Yeah.
flow. Yeah.
Yep. I think in Aviation Weather Handbook, I think there's a really good diagram of that. There'd actually be one in here.
That's cool. Well, I'm sorry Kevin and Sophia couldn't make it tonight because I think they had the bulk of a lot of the questions and stuff like that. So hopefully,
I had a question.
Yep.
What would you recommend to, I guess, any of us or anyone in general who wants to get a better idea for this stuff on just like a day-to-day basis, you know?
Great question. I was hoping somebody would had a whole like preamble. Yeah, I mean, one, always consider me a resource. Like, I feel really fortunate that I grew up in Iowa living on a farm, and every day your livelihood depended year-round on what was happening with the weather, winter or summer. And then I got to do that in the Air Force.
Yeah.
And so when I started flying, I didn't have to learn weather. And I can't imagine how difficult that must be for, like, I wrote TAFs, so I didn't have to learn how to decode a TAF. I made airmet and SIGMET charts, so I didn't have to like figure out what was going on or what was driving those. So one, know that I am a resource and happy to take time with either you or students to make any weather concepts more clear.
Thanks.
And even if I don't have the answer on the spot, I know where to look up almost any answer that we would need to find for weather. So on a personal level, how do you make yourself better at just understanding what's happening with weather? So much of it's just getting familiar with what's happening where you are. So, and I think I mentioned this once before, every morning read the forecast discussion. And I read it every morning. The other thing that I do, my espresso machine takes 30 seconds to pull a shot. So while I'm standing there waiting for it in ForeFlight, I have all of our local airports pulled up so I can really quickly see like, oh, what's happening. Especially summertime, I'm always very interested in like what's happening at Marina versus Monterey. Fascinating, the difference that can happen there, and even Watsonville, but what's happening here. So kind of just keeping an eye on like what is the weather doing throughout the day. Definitely reading the forecast discussion. Like I don't often, unless there's actual weather happening, I'm not looking at radar every day. I like to look at satellites because it's fun, but like I don't look at it every day because normally there's not really, for us, too much that's interesting.
Yeah.
And then I think I'll see if I can find some of the better like the West Coast like kite surfer blogs, because they do a really good job of talking about the little like micro perturbations that are happening on the West Coast, or like some of the surf blogs are actually really good at it as well. Like, and I know one of the questions was like, how do we understand the impact of like climate on our weather? There's a called Surfline or no Storm Surf. There's a website and an Instagram account called Storm Surf. The guy's a surfer, but he's constantly looking at what is happening all the way across the Pacific over by Japan to figure out when we will have good swells here. But he's also really tuned into ocean temperatures and the influence of the Southern Oscillation on El Nino and La Nina. So he's normally making the call on what's going to be happening for the winter before National Weather Service issues their El Nino or La Nina forecast for the year. So there's some of those things where you kind of just have to like poke around and like, what is it that you're trying to get familiar with, and see if somebody else, like who else would be a consumer of that kind of weather information, and see if you can find it.
So I have two questions, and I don't know when to tie anybody else's time, but like, what do you feel like is the best starting point to start teaching a student about weather?
I would probably start with what we're talking about, like private pilot students. It's probably like
from a concept, like what?
Oh, concept.
Yeah.
I'm gonna say like I would start with just like, let's look at the METAR, let's look at the TAF, let's just start to get familiar with what does that mean and what's happening. The other thing that I would probably start with is, I think one thing that's important is they need to get familiar with what's on Aviation Weather Center. Eric and I've had discussions about how worthless this site is, but at the same, I bet, see now I said that and I won't even be able to find the thing that I'm looking for. Where's the surface?
Right there. You just gotta click that little box there. And then it's pull up the WC bug chart.
Clear selection.
They just,
Yeah.
current forecast,
Never mind.
Look what I did there.
I'm a computer.
This is this is
High low, high low, high
this is
low.
actually
MS
hold on.
Paint.
Alright. This was not like what picture did I have up here? I literally pulled this from I guess it is kind of a little bit of alphabet soup there.
High low, high low.
This isn't helpful at all. Because what I would say is like just get them familiar with looking at weather and what's happening and what are you seeing over time.
Do you think maybe just the NWS site is a better one to use? If you're not looking at it for specifically an aviation perspective, but just kind of in general is like, oh, I want to know more about what's going on here.
Yeah. I mean, how did I get there?
I think the NWS site focuses first from a standpoint of like safety, like warnings and all that kind of stuff, and you have to dig deeper to get into like data, observations, that kind of stuff. So
Yeah, I don't know that I have a good answer to that question yet.
So, like, what I always, like a lot of times when you read about weather to learn about it, it starts macro, like just huge macro, trying to get big understanding of what's going on with the weather, and then it kind of whittles its way down. But what I found in teaching some students is that it's way more effective to teach them about the micro, like about the local advection cycle that happens every day that they
need to be able to understand, like if you're explaining a concept to them, they need to be able to experience it.
Yeah, exactly.
Yeah.
And like the macro level, they have a harder time relating experience to like the day-to-day.
I also imagine that for kids that have grown up here, it must be so hard to have them understand like like when you live in the Midwest, you know what a cold front is, you know what a warm front is, like you live it, like, and you can tell the difference. And out here, you're like, oh, it's gonna rain, and you don't really even know like, is it raining because of?
That's 70.
When we get like the inside slider, that'll just destroy us with the rain. But in terms of what you have to learn for like aviation weather to pass a check ride, the concepts that are causing it to rain are not the concepts that you need to know to pass that check ride, which is kind of tricky.
Yeah. The other thing I was going to ask you is, like, if somebody wants to learn more, like say they're a CFI or something like that, and they want to learn more, like, would you recommend a specific book or the Penn State thing you mentioned?
The Penn State one is really good. There's a couple of those. There's National Weather Service has what they call Jetstream, which I think is actually too basic. It kind of glosses over some things. There's a couple of things where I'm like, is that right? I'm not sure that it is. But it's generally like, it's going to give you enough to be dangerous. The Penn State one is really good. And then if you want to go deeper, there's, I have a couple of them open up on my computer. There's a website called Habby Hints, Habby Hints. He's named after a guy named Jeff Habby, meteorologist, where he goes, if you want to go deep on vorticity, his vorticity page is fantastic. And those pencil diagrams, I think, that I had up there were his. So yeah, there's places around where you can find it. I haven't found a good aviation weather one yet, although the AOPA one is actually pretty good. And it actually puts you through modules and they're free, that you can then ask some, there's questions that you can answer at the end. So kind of test your understanding.
Cool. Well, thank you, Beth, very much.
Thank you.
Excellent.
Yeah, this is great.
I think when we started talking about teaching this for the CFI group, like when we had Adam and Sophia and